Бородатого времени суток, дорогие друзья, вы слушаете 333-й выпуск подкаста «Теория большой бороды», самого научно-космического русскоязычного аудиошоу, которое веду для вас я, Антон Поздняков. И сегодня у нас снова выпуск с представителем Дармского университета, моей альма-матер. В выпуске с красивым номером 300 мы говорили с профессором Карлсом Фрэнком, тоже из Дармского университета, о вычислительной космологии, о лямбда-CDM-модели. Обязательно послушайте, если пропустили. Один из лучших выпусков, если не всей истории теории большой бороды, то точно прошлого года. А сегодня мы поговорим о компьютере, на котором это все разрабатывается и вычисляется. Если конкретнее, то о суперкомпьютере COSMA, который уже много лет стоит на службе космологии. Ну а делать все это я буду в рамках нашего большого проекта, в котором я рассказываю о, как мне кажется, главных вещах, которые формируют будущее науки и космоса. Делаем мы этот проект вместе с компанией Selectel. В первом выпуске этого цикла я рассказывал о космическом интернете, как он работает сейчас, как он будет работать в ближайшем будущем и как он будет впоследствии менять целые индустрии. Это было в 329-м выпуске, а сегодня, как я уже сказал, поговорим о том, как суперкомпьютеры формируют будущее астрономии и космологии на примере конкретного суперкомпьютера COSMA. Ну и вообще, компьютеры сейчас используются не только в астрономии, но и, наверное, в любой науке. Есть в том числе куча гражданских проектов, когда в научных исследованиях участвуют добровольцы, даже не имея специального образования и особой подготовки, а предоставляя там свои вычислительные мощности или свое время. И Selectel активно поддерживает такие инициативы. Например, есть такой проект, как Experion. Это платформа для анализа научных изображений. Волонтеры могут зарегистрироваться там и размечать изображения, необходимые для обучения нейросетей. И для работы платформы и хранения тысяч космических снимков Selectel бесплатно предоставил проекту свои выделенные серверы, что вообще очень крутая инициатива, которую я всячески приветствую. Ну и глобально вычислительных мощностей Selectel может хватить для создания сразу нескольких суперкомпьютеров. Недавно компания вошла в топ-3 крупнейших операторов дата-центров и уже сейчас предоставляет мощные выделенные серверы под особенно требовательные задачи. Вот такой у проекта у нас классный партнер. Ну и теперь давайте поговорим непосредственно о COSMA, о том, как он устроен, на чем работает, какие у него есть особенности и обо всех остальных интересных аспектах. Это оригинальная версия, интервью на английском, также доступен перевод на русский, это соседний выпуск в фиде, так что если вам он более удобен, пойдите и послушайте его. So, today I'm joined by Dr. Alastair Basden, who is based in Durham, and who knows everything about the COSMA supercomputer that's located there that we mentioned in one of the previous episodes. So, hello, Dr. Basden.
Hello, thank you. I don't think I know quite everything about COSMA. There's lots of hidden things that no one seems to know, but anyway, close.
Okay, can you then please tell us a bit more about your role and what you specifically do with COSMA?
So I'm my official job title is HPC Technical Manager, and what that means is that I manage COSMA. I run the team that look after its day-to-day operation. I am responsible for future installations, for forward planning, basically maintaining a system that users can use and want to use, and one that makes it easy for them to use, so that, making sure that the right software packages are in place, that people can get into it as they wish, and things like that. So on a day-to-day basis, I will typically, in an average week, I'll typically spend some time in the machine room, in the data center. It might be fixing things that are broken, or it might be installing new kit, and then the rest of the time will be spent perhaps answering help desk queries, we'll be installing new software, checking that the machine is operating as it should, and planning for future installations.
So, as I said, we've already mentioned COSMA in one of the previous episodes when I talked to Dr. Carlos Frank about the lambda-CDM model and how this whole thing progresses and how computational cosmology works in general. So, let's dive a bit deeper in what COSMA is and what problems is it designed to solve.
Okay, so COSMA is short for the cosmology machine, COSMA. And it's a high-performance computing system, which is now in its 8th generation. The first installation, COSMA 1, it was actually just called COSMA then, was around the turn of the millennium, 2001, I think. And since then, we've had multiple generations of systems. So the first two were based on Sun Microsystems processors, so Spark processors. We then moved on to the third system, I think, was an AMD Opteron system. That was COSMA 3. So COSMA 4, 5, 6, and 7 were all Intel systems. And COSMA 8 is now an AMD system again. We currently have 4 generations of the system are up and running. So COSMA 5, which was first installed in 2012, is now approaching retirement, but hasn't yet been retired. COSMA 6 is actually of a similar vintage. It's got an interesting story. It arrived in Durham second-hand in 2016. It was surplus to requirements elsewhere. It's very similar hardware to COSMA 5, though it's a slightly larger system, so that's COSMA 6. Now, COSMA 5 is one that is wholly owned by the Institute for Computational Cosmology at Durham University, so it's just used by ICC members and their collaborators. COSMA 6, 7 and 8 are part of the DIRAC National Facility, so it's funded by the UK Science and Technologies Facilities Council. So COSMA 6 arrived in Durham in 2016 and is still in operation. COSMA 7 arrived in Durham in 2018 and is approximately 450 nodes of Intel Skylake processors, so 28 cores per node. And then COSMA 8 went under the start. We received funding for COSMA 8 just less than a year ago. We went through a procurement process. It's now been the bits kind of arrived early this year. We racked them up, we wired them together, cabled them together, installed the software and that sort of thing, powered it up, and it's gone through its acceptance. It's been accepted, and it's now going through what we're calling a commissioning phase. So this is where we want to check that the system really is ready for new users. So we're running some large science runs. We're testing various different aspects of the system. So can we run large jobs for long times across the whole system? Is the software stack acceptable and usable, etc.? And then it will go live to the general audience at the start of October. So that's when we release it to DIRAC users. So that's a brief summary of COSMA through the ages up to the latest COSMA 8 system.
Yeah, and what's it like physically? So how much space does it take? How do you replace each generation? Do you just keep the old one and put the new one near it? So just to give our listeners an impression what it's like, because, when they hear about a supercomputer, they probably think about, some huge black boxes in some basement, which are, they have blinking, usually green lights if everything's okay, hopefully no red lights, and that's how people imagine a supercomputer. So how close is it to a actual thing?
Yeah, so essentially it is a bit like that. It's certainly you're in a windowless room. It's not actually underground. But it is ground floor, so it does feel a bit like a basement. It's very loud in there. There's lots of fans from these servers blowing to keep them cool. And we've actually got two machine rooms, 2 data centers. The first one was the original one, and that hosts COSMA 5 plus various other university facilities. Then in about 2015, we started work on a new data center, and that's the room that hosts COSMA 6, 7, and 8. And so what these systems look like is, so COSMA 6, for example, is a load of compute nodes, which are basically 1U nodes, so that's 4.5 centimeters high by about 50 centimeters wide. So that's one compute node in that. So it's kind of
pretty much like a server rack.
That's a server rack, yeah, that's right. So we have lots of server racks, each with these 1U servers in them, and they are connected to a high-performance fabric, so a high-performance network, which for all the Cosmos we've got at the moment is InfiniBand. That's provided by Mellanox, who have recently been taken over by NVIDIA. So each node basically has 2 fabrics. So it has a low performance Ethernet fabric, which is just used for SSHing into the nodes for management, etc. And then has a high performance fabric, which is this InfiniBand fabric. So COSMA 6 has a number of racks. I have to say probably about 8 racks, something like that, of compute nodes plus a rack of storage. So this is lots and lots of hard disk drives, basically filling up a rack. So, up to about 2 meters high, full of hard disk drives. And that then is presented to the compute nodes over this InfiniBand fabric to look like a single file system. So just a single file system that's several petabytes in size. COSMA 7 and COSMA 8 are slightly different. The compute nodes there are only half the width of the COSMA 6 compute nodes. So it means we get 2 compute nodes per rack unit. So it's what we call double density servers. So it increases the number of servers you can get in a rack, reduces the floor space you actually need. So COSMA 8 is comprised of about 8 racks of compute nodes and 2 racks of storage. And so it's about 450 compute nodes there. So that's COSMA 7, and COSMA 8 has similar. From the outside, the compute nodes look very similar to COSMA 7. They're both Dell kit. They've got, they look kind of, the boxes look the same, but on the inside they're quite different. So COSMA 8 has 128 processing cores per node, a terabyte of RAM, and 360 of these compute nodes. So it's about 45,000 cores available to COSMA 8 users. And because we're a system that focuses primarily on cosmology, so we're generating simulations of the universe. So we start with the Big Bang, we explode the universe and propagate it through time. Because we're doing that, it requires storing all these different particles. It requires a large amount of memory, a large amount of RAM. So COSMA, throughout its history actually, has been a capability system. So it's had a large amount of RAM per compute node, currently a terabyte of RAM per compute node, which is typically a factor of 4 larger than your average HPC system. And so it means that although we perhaps don't have as many compute cores as some of the larger systems in the UK or in Europe or in the US, we can actually do larger simulations than much larger conventional HPC systems because we've got this extra RAM that we can fit data in. And so then you need fewer cores because the data is all there together. So COSMA 8 has 5 racks of compute nodes and then 3 racks of storage. It's got about nearly 6 petabytes total of storage. One of the things that makes COSMA 7 and 8 special is they both have what we call a snap storage file system. So it's a very fast file system, which is designed for as these simulations are being generated. Okay, so you're propagating forward in time from the Big Bang. Every so often, you write to disk what's called a checkpoint. So you write the entire RAM of the system to disk, which means that if something goes wrong with the simulation, you've got somewhere that you can start from. Now, dumping that to a conventional file system is going to take a long time, so there's a lot of RAM to write. But because we've got these snap file systems, that reduces potentially by a factor of 100 or so the amount of time taken, so you can then get on with running your simulation much more quickly. So at one point, the COSMA 7, when it was installed, the COSMA 7 scratch file system was actually the fastest in Europe, and the COSMA 8 scratch file system is effectively a factor of 2 larger and faster than the COSMA 7 one. COSMA 8 has an InfiniBand network, which is 200 gigabits per second. So and every node is connected in a non-blocking fashion to every other node. So it means that data can flow very quickly between the nodes as required to share these particles, the particle information of the universe between these different nodes.
So when you said how the different generations were different, you specifically mentioned the CPUs, so the brand of the CPU. Does it mean that the main thing about simulations is cosmology is actually CPU bound rather than GPUs? Because I think, again, a lot of listeners would probably guess that if you're doing simulations that do some 3D space stuff, it's I think supposed to be done on a GPU, but it seems like that you do that on a CPU. Is there a reason for that, why GPUs are not that good for these kinds of simulations?
Yeah, that's right. So COSMA doesn't really have many. It has a small number of nodes something like 5 nodes or something, which have some GPUs, and they're generally used for. They're not used for the bulk of the cosmology work. They might be used for some AI work, perhaps analysing some of the data that's been generated and things like that. But so the bulk of the cosmology work is, as you say, done on CPUs, and in part that's because you've got all this data that you need to share that's in the RAM. It's far too much data to put in the RAM of a GPU. Okay, so if you were going to use GPUs, you have to take this particle data from the CPU memory into the GPU, back again. You might also need to send it to other nodes across the fabric. And in the past, certainly what we found is that it has not been effective to use GPUs. So it's actually using a GPU has slowed it down. Now, we do have a program of work at the moment it's looking at using some of the newer GPUs to see whether we can get a speed up from GPUs, whether it actually becomes cost effective in the future to have a GPU enabled cluster. That work is at the moment in fairly early stages.
So am I right that the main bottleneck was between the actual CPU and the GPU, so the lanes between those two, that bottlenecked the whole system and limited what you can do?
Yeah, or more strictly speaking, between the RAM that's storing all this data and the GPU. So you know it is possible to transfer from RAM into a GPU bypassing the CPU these days with GPU Direct and things like that. But that still it becomes your bottleneck.
Yeah, and again, in terms of bottlenecks, is that correct? That pretty much any supercomputer is basically bound to the not to the number of the CPU units that it has or GPU units that it has, but it's about the interconnection between those. That's basically the thing that makes a supercomputer work, to put those things all together. Is that correct?
It very much depends on the type of simulation you're trying to do, actually. If you're trying to do what we call massively parallel workloads, where the code itself is a self-contained unit that can run on a single GPU or a single CPU and so on, and doesn't really need to talk to other CPUs, but you just need to run lots of them, thousands or millions of them, then they don't need to talk much to other nodes. So then something like that is actually a good match to, say, a cloud-based system, AWS or something like that, where each node is isolated, so you don't need a good fabric going between the nodes. Now, for something like cosmology, because a particle over here, the gravity, for example, of a particle over here can affect other particles way over that way, you do need to transfer all this data between these different nodes. So you've always got stuff flying around, and that's where having a high-performance fabric is important. And it's not just the bandwidth of the fabric that's important, it's also the latency. So how the amount of time it takes to get a message, could be a small message, from this node to this node over here. So from one node to another node, and perhaps back again. It's not just how many messages you can get through, but or you know how much data you can actually pipe through, but actually the length of time between sending a message and it being received.
Does COSMA, as a computer that does specifically cosmology, does it need to be built in a special way compared to other supercomputers that do other kinds of simulations? So we've talked about, so it's mainly CPUs, it has the infinity fabric between them. Any other architectural, structural things that need to be different compared to other supercomputers that may do any other kinds of science, or maybe not specifically science, but other sort of simulations, calculations, etc.
So the network interconnect is probably the important thing, and actually it's InfiniBand rather than Infinity Fabric. Infinity Fabric is...
Oh, sorry. I think Infinity Fabric is the AMD term for how they stack their cores.
That's right. So Infinity Fabric is what's done within an AMD chip, or perhaps between two AMD chips on the same motherboard. So no, InfiniBand is the fabric that we use to between the nodes. And now a lot of HPC systems that don't have such a requirement for a network as we do will use what's called a blocking fabric. So you'll have a node, but the nodes are connected to switches. There's then a second layer of switches, or perhaps even a third layer, depending how large the cluster is, which each switch is connected to. So it's kind of like looks a bit like a tree. We call it a fat tree topology. And the number of, you can save a lot of money by reducing the number of links between switches. And it can be very cost effective to do that if you don't need to transfer data all the time between all the nodes. Now, for us, this data transfer is very important. And so what we have is we have a non-blocking fabric, which basically every switch is connected to it will have a certain number of connections going to the nodes, the compute nodes, and it will have the same number of connections going to the next level of switches. And that we call a non-blocking fabric, because it means that you've got the same bandwidth into the switch as you've got going out of the switch. So that's one of the considerations that we had to do for this design.
Okay, and what sort of maintenance does a supercomputer like that require? You know, it's a big machine, so I assume there are lots of things that you need to do to take care of it.
Yeah, that's right. There's more that can go wrong than you might first think. So the first thing that can go wrong is nodes can crash. So if they're running a large job and a node crashes for some reason, now sometimes it's because the job is using too much RAM, and then perhaps some of the network drivers aren't able to cope because they've been starved of the RAM and everything goes wrong. It can be various other reasons as well. So sometimes the nodes reboot themselves, and then you just in a software problem, you just have to bring those nodes back online, check that they're okay, and put them back into service. So that's the first thing that can go wrong. Another thing that's fairly common is memory can go wrong. So each of these servers has 16 DIMM sticks of RAM, and you know the connections of those can go wrong, or the chips on them can go wrong, and so from time to time these will need replacing. Other things that can go wrong, the disks hard drives can fail. So if we've got spinning disks, we typically have maybe between 5 and 10 failing per year. So not a huge number, but it's enough that we have to keep an eye on it.
Does it run some sort of RAID configuration then?
That's right. So our file systems are based on Lustre, which is a parallel file system. And they have redundancy that effectively uses a RAID system. So if a disk fails, we're okay, we can replace that disk. If 2 disks fails, again, we haven't lost data. If 3 disks fail that are in the same logical unit, the same partition, so a partition in our systems is typically about 12 disks inside. If 3 of those disks fail, then we've got problems, then we've lost data. Fortunately, that hasn't happened yet. Now, of course, if 3 disks fail across the machine at the same time that are in different partitions, again, we haven't lost data because each of those will be able to rebuild itself.
Will you have any benefit in some future time switching to SSDs rather than spinning disks?
So that's right. So I mentioned earlier the fast scratch or snap file systems that we have. They are based on NVMe drives, so SSD drives, and that's where they get their speed from. Currently, it's still a more expensive way of doing things. So for the bulk storage, we build that out of spinning disks. Now, at some point in the future, it may be that solid state storage becomes cheaper, in which case we would then move entirely to solid state. And we see that the failure rate of solid state is probably better than for spinning drives, I guess partly because there's no moving parts. The other thing that I haven't mentioned yet that we use for long-term data storage is actually tape drives. So we have a tape library, which basically has a number of tape readers. So these are kind of systems little boxes that sit there, and we have a robot that moves around and can move tapes into these libraries. And we generally use that for archiving data. If we've got data that we want to keep for a long time, that will get archived onto tape, and then in, say, 10 years or something, it's then accessible. And one of the benefits of tape actually is that it doesn't have any power consumption. So we can just have these tapes sitting there, and when we need the data off them, we put them back in the drive, and only then do they start consuming power again. So it's a good way of managing long-term storage.
Do you store the whole thing? So you mentioned that you have about several petabytes, which I assume is all used for a simulation for a one run. So do you keep all of that, or do you just keep any slices of the information?
So when a large run is done, typically we keep all of that information, we back all of that information up onto tape.
As far as I know, the only downside of tape in terms of long-term storage is that it takes a lot of time to actually read and write to tape.
That's right. So you certainly don't get the performance that you get from our online file systems from tape, but it's the sort of thing that, you know, if you've got a large data set that you want writing to tape, you'll just set it going, you'll forget about it, you'll come back a couple of weeks later and it'll be on tape. If you need that thing bringing back off tape, So back onto your online storage, again, you have to plan in advance, and you say, okay, well, I want this data set brought back live. You set it going, and then depending on the size of the data set, of course, it can be up to a couple of weeks before all the data is finally back on the system.
Do you back it up somewhere else, or is it just one place with one tape?
No, we have the redundancy of the RAID systems, which keeps us safe for disk failure, and then the tape system, which is used for this long-term archive.
Okay, and how often do you actually run the big simulations? So what sort of cadence do you have between those runs, and how often do you actually change what runs on the supercomputer?
So it varies a bit, but for what we call a large capability run, they would typically be done maybe every 2 or 3 years, something like that, on a run that will take up the whole cluster for months. Then the rest of the time is spent basically analysing that data, comparing it with what we see in the real universe and things like that. And then also during that time, we will also do smaller simulation runs that, perhaps investigate some new bit of physics or some new parameter set that we want to explore, things like that. But the largest runs, typically every 2 years or something like that, perhaps.
Yeah, so in general, on an average day, how much computational power is actually used on COSMA?
It's all the nodes are in use all the time, basically. So we have a queue system to which users submit their jobs. So they've got some work needs doing, they'll submit their jobs, and then when nodes become available for those jobs will then run. And the queues are always there's always a waiting time on the queues.
One thing I didn't actually ask, what sort of software does it run on?
So the operating system, it runs Linux, and then the way these systems are used is users will access what we call a login node. That will then give them access to compilers and things like that, and also the queue system. So they'll get onto a login node, they'll perhaps prepare any configuration files, they'll compile their codes, they'll perhaps even develop their codes on the login nodes. Once these things are ready to go, they will then submit a job to the queue system, which then allocates the right number of compute nodes for that job to run on.
And what sort of code does it need to run? So what sort of simulations does it usually run when students or researchers do that? Does it have to be a specific format? Does it have to be a specific language or something like that?
So there are a number of cosmology codes that are used by the community. Probably the major one that's used here is called Swift, which is
not the Apple language.
No, it's a cosmology code, and there are a number of other ones as well. Arepo, Gadget, and various other ones. And typically, the way it will work is a new student or researcher will download this code from GitHub or something like that, from a repository somewhere. They will then compile the code, test that it runs, test that they know how to run it, etc. If they're doing development on this code, like introducing a new bit of physics or something like that, they'll then be developing the code, compiling it, and so on, playing around with their parameter files, their input parameter files, and so on. And then when they're ready, they'll launch these jobs. And so most of these codes are written in C or Fortran.
Fortran is a bit of a stretch, to be honest, I think, in the modern world.
It is, well, no, you'll be surprised, actually. It's still very widely used within the scientific community. A lot of codes still use Fortran.
And I think it's just when it comes to programming languages in science, I think a lot of our listeners would expect something like Python. So it's just I know that Fortran is actually generally used, and in astronomy, I know that a lot of people use actually quite old programming languages because that's how things work for now. But I think for a lot of our listeners, it might be a little bit of a surprise.
Yeah, that's right. So we do have Python usage. It's not used for running these initial simulations, but it's sometimes used for analysing the simulations afterwards, and also for sometimes for setting up the initial conditions for these simulations. So when you're preparing a simulation, And also it's very good, obviously, for visualization and things like that. So that's another use for it. So for analyzing a data set, looking at a particular area of the universe, perhaps at a particular time. So, but it's generally not used for running large simulations itself, basically because it's less efficient than compiled languages such as C and Fortran. So, if you were to run a job in Python doing the same thing, it would require more RAM. It would also take a lot longer, and so it would be an inefficient use of time and resources.
So what's next for COSMA? It's being upgraded recently, as we've found out.
That's right. So the COSMA 8 hardware is relatively new. It's going to be put into full production in October. Is the current plan. Now there is potentially an expansion phase of COSMA 8, which will take it up to about 600 nodes. And that may be within the next year or so. We're still waiting to see whether that's going ahead. Beyond that, it will depend on funding when we get COSMA 9.
Yeah, and by the way, why did you transfer to AMD again? How did the evaluation process go? What made you switch from one vendor to another one?
Yeah, so we had at the start of this procurement cycle, we had a benchmarking phase where we took a number of the different scientific codes that run on COSMA, and we benchmarked them on different CPUs, so different vendor hardware. Now, some of those we had access to, others we didn't, and so the CPU vendors themselves were running the codes on their hardware. And then we collected all these results together, and it then gave us information based on the cost as well about which processor was most suited in terms of performance per cost, and the AMD system was the one that came up here. And now one of the things that's slightly special about this AMD system is it's the first system we have that uses direct liquid cooling. So this is where the heat that the CPUs generate is taken away not by fans but by liquid.
Can you actually repurpose it for, let's say, heating?
So this liquid, at the moment, it's taken away. It then is not repurposed for heating. It's typically somewhere between 20 and 30 degrees, so it's at a lower temperature you would have in your radiators. So if you wanted to use it for heating, you would need underfloor heating, which obviously is for a building that's not designed for that, is a large infrastructure project. And again, it's something that would only be useful for typically half the year or something like that, because obviously in the summer it's too hot to heat your offices. But it is something that personally to me is something I am looking at ways that we can make use of this heat, not for this particular data center, but for future data centers. I think we have to be asking ourselves, what can we do with this heat that's generated, and how we can configure the data center so that the heat the water has a higher temperature, so that then it becomes more useful for things like heating buildings and so on.
Yeah, and it's basically not just about the efficiency and all this green stuff, but it could also probably save quite a lot of money for the university in terms of if you repurpose the heat that you're generating from the electricity that you already paid for the run of the computer, you can then just save something on the heating of the building, which in the long term can be quite beneficial. And in terms of switching the vendors, does it actually cost anything to switch from one system to another in terms of optimizing software and stuff like that?
Only in terms of the effort that it takes us to get used to a new system. So if we were to switch vendor, typically they will run the same or very similar software. There'll be, our current systems are all x86 compatible systems, so it hasn't really cost anything to switch between Intel and AMD because the processors are effectively compatible. They'll run the same binary codes, with a few caveats depending on how the optimization is done. But there is more of a, if we were to switch server vendors, which we do periodically, there is more of a cost associated with that, because then these different servers have different management software that we then have to learn and adapt into our system.
Did you look into switching to in IRAM-based processors? Because that seems to be where everybody's going right now. And I've heard that supercomputers are already running on them. So
that's right. So within Dirac, at one of the other Dirac sites, we do have an ARM cluster. It's not something that we have here because at this particular procurement it wasn't cost effective. Our codes are known. The main codes that we use on COSMA are known to run on ARM systems, though the optimization, etc., of those hasn't. I don't think we've done a full. We haven't investigated how they run fully optimized, etc. But I suspect at some point in the future we may well move away from x86. We haven't. For the history of COSMA, it hasn't always been x86, but we may well move to ARM or to something else.
What do you expect in terms of results? What are your personal expectations? Are we looking forward to any discoveries or any new results from the simulations that we'll get that will change our view? Maybe we'll finally find the dark matter particle, or at least narrow down where to look for it.
That's always the hope. The aim of these systems is to be discovering new physics. Let's hope that happens. And in the past, of course, when we've had other large runs, they have brought out new science and new discoveries and so on. So, there's no reason that won't continue.
Yeah, and in terms of the absolute next simulations, so what sort of difference will it make? Will it be greater resolution or something like that? So, or maybe you'll be able to add more particles. So, what will change in terms of simulations with the generation leap that you've done?
Yeah, so the main thing is the much larger number of particles. We will be having runs that are using a trillion particles and things like that. So it's a lot of particles to play around. But that then allows us to look at the universe in a greater resolution, a greater depth, and over a greater volume of space. Because we've then got better statistics, we then are able to fine tune more of the science that goes into that and really draw limits on the mass of certain particles, on the amount of dark matter and things like that.
Okay. I think on that optimistic note, we can end our conversation today. Thank you very much for your time. It's been an absolute pleasure talking to you, and thank you for letting us know a bit more about the supercomputers that shape how cosmology progresses.
Okay, pleasure talking to you too, and thank you for your time.
Что ж, вот такой у нас получился выпуск. Вот так устроен, собственно, суперкомпьютер, который формирует будущее космологии, компьютер COSMA. Надеюсь, теперь у вас есть лучшее понимание о том, как это все работает. Мне очень понравился выпуск. Надеюсь, вы разделяете мои чувства. Напоминаю, что это часть большого проекта, который мы делаем вместе с компанией Selectel. Selectel вообще крутые ребята. Они поддерживают кучу инициатив, о которых я уже рассказывал в начале. Ну и в том числе они поддерживают такую крутую инициативу, как этот большой проект. Так что если вам нужны какие-то IT-услуги, если вам нужна IT-инфраструктура, развернуть свое там приложение, может быть, по работе вам что-нибудь нужно, вы знаете, к кому обращаться, ссылочки есть в шоу-ноутах. Ну, а также я вам напоминаю, что вы можете поддержать теорию большой бороды, сделать это несложно, нужно всего лишь поставить какую-нибудь оценочку, а еще лучше написать отзыв в таких приложениях, как Apple Podcast, CastBox. Можно сделать все ютубные ритуалы, если вы из тех, кто слушает этот подкаст на ютубе, а такие среди вас тоже есть, пусть вас и значительное меньшинство, но кому-то удобнее слушать на ютубе. Если так, то ставьте там лайки, комментарии, подписки, вот все вот эти вот вещи, вы и так в курсе, что надо делать. Ну а если вам совсем-совсем все нравится и вы хотите получать дополнительные выпуски после шоу от теории большой бороды, ну и также просто сказать спасибо проекту в виде небольшой денежки, сделать это можно двумя способами. Во-первых, в Apple подкастах, там есть отдельная кнопочка теперь, поддержать теорию большой бороды, будете получать выпуски после шоу прямо себе в ленту. Ну, а также вы можете это сделать через платформу Patreon, там чуть более гибко все, и там заодно есть другие наши подкасты, так что либо Apple подкасты, либо Patreon. На Patreon просто выбираете тариф, который содержит теорию большой бороды, получаете выпуски после шоу, получаете доступ в телеграм-чатик наш эксклюзивный. Кстати, если вы хотите попасть в него, поддерживая подкаст на Apple подкастах, напишите мне в личку, я вас туда пущу, потому что там Apple не предоставляет такой функциональности. Так вот, выбирайте тариф, содержащий теорию большой бороды, и все работает. Ну и, как всегда, отдельное спасибо тем, кто поддерживает все наши подкасты, всего нашего большого проекта на Патреоне, на нашем самом большом тарифе Бердикаст Плюс. А делают это такие замечательные люди, как Анатолий Брощик, Артем Баулин, Артур Алиев, Алия, Атлантий, Богдан Пришедько, Владислав Михалев, Григорий Кимов, Григорий Меликесцев, Дима Гиря, Дмитро Лапа, Джаггер Меш, Евгений Бразгин, Иван Рубановский, Лип Фиц, Михаил Соколовский, Михаил Столович, Николай Панов, Неткрафт Компьютер, Сергей Мещеряков, Максим Казаченко, Машин Learning подкаст, Рубен Алексанян, Владимир Холоповских, Александр Фищенко, Станислав Островский, Сергей Силаев, Сергей Селедько, Ярослав Почернин и Валерий Игуменцев. Присоединиться к этим людям можно по адресу patreon.com/birdicast. Ну а на этом я с вами прощаюсь. До новых выпусков, до следующего четверга, да пребудет с вами сила и пока-пока.